Buenos días a todos. En primer lugar, pues quería agradeceros a todos, quería dar las gracias a todos por venir a la presentación de hoy del seminario del doctor Cerri. Un par de detalles antes de empezar. Primero, un poco marcar este seminario, por qué le hemos traído, quién lo ha traído y sobre todo a la gente que esté interesada del doctorado de Ingeniería Eléctrica, Electrónica y Automática, para decirle qué procedimientos tiene que seguir para registrarse en el seminario, que bueno, que hay un poquito de dudas con eso. Y en segundo lugar presentará a nuestro ponente de hoy. Como os comentaba, este seminario forma parte del doctorado de Ingeniería Eléctrica, Electrónica y Automática. Me gustaría recalcar un poco esto porque es la primera vez que hacemos un seminario de este estilo en el doctorado y hay ciertas dudas. Bueno, simplemente deciros a los que estéis matriculados, si os interesan estos créditos, que haremos una hoja de firmas al final en la que todos os podéis registrar y luego ya nos pondremos de acuerdo con el CAES porque ha habido pequeñas dudas con eso. Pero bueno, no os preocupéis que esa es la forma que tendremos de hacerlo, ¿vale? Entonces, cuando termine, acercaros por aquí, que estaremos pendientes de todos los que estéis registrados para tomar nota. Con respecto a esto, pues también queríamos agradecer desde el Laboratorio de Sistemas Inteligentes de la Universidad, del Departamento de Automática, a todos los encargados, tanto los directores del programa de doctorado como los del CAES, la gente del CAES que nos ha permitido traer a mi compañero Pietro al día de hoy a hacer esta presentación. Pietro es compañero del laboratorio VisLab de Parma, de la Universidad de Parma de Italia. Él es doctor allí, es uno de los, digamos, no sé cómo decirlo, jefe de sección o jefe de grupo, que está encargado de algunos de los proyectos más interesantes que tienen allí con relación a vehículos autónomos. VisLab's lleva trabajando en temas de vehículos autónomos desde la década de los 90, que fue cuando hicieron sus primeras pruebas de vehículos autónomos, hasta la actualidad, justo este verano, cuando hicieron la última de las pruebas, que es una de las cosas que voy a presentar hoy, para que no os voy a desvelar nada, que ya será el encargado de presentarla. He tenido la suerte de trabajar con el grupo VisLab en 2 ocasiones y espero pronto va a haber una tercera ocasión. Hemos hecho un montón de trabajos juntos. Pude aportar mi pequeño granito de arena, pequeño, pero bueno, está ahí, en el proyecto de Brave. Y bueno, para mí es un placer haber podido invitar a Pietro, que me ha ayudado muchísimo durante el desarrollo de mi tesis doctoral y ahora en el postdoc. Y bueno, nada más, espero que os guste. Hemos hecho un esfuerzo grande para traerle aquí, la universidad ha hecho un esfuerzo grande para traerle aquí. Y sin más, le doy la palabra al doctor Pietro Cerri. Pietro, please, you are free to start.
Okay. Thank you everyone for being here. Thank you, Dr. Garcia, for introducing me. Okay, today I will speak about autonomous driving. I will give you our point of view, the point of view of our lab, and I will speak about our experience, our test, and I will also give you some detail of our last experience of our last test, and I will also give you some idea of what we are planning to do. Okay. Okay. What we are talking about? We are talking about autonomous driving, not remote control, not someone hiding in the car and driving. If you know supercar, the series in the 80s, there was this supercar, and there is a little boy driving the car. Okay, this is not our cases. Okay, this is not our case. We want to replace the driver. We want to have no driver behind the steering wheel. Okay, and why do we want to replace the driver? Okay, I show you 3. Okay, it seems funny. In this case, are funny. Okay, in our case, it's not so funny. And okay, let me say, the driver can do error. We know it. I'm very tired. I'm watching at my mobile. I'm watching at the radio. Okay, I can do some error. Okay, so we want to replace the driver and of course, to reduce the accident. Okay, I will show you a very short video and about something that happened in 2004. Okay. Okay.
Ladies and gentlemen, Sandstorm. Virginia Tech's Cliff. See you, Bob. Ladies and gentlemen from Caltech. See you, Cliff, Bob. University of Louisiana, Lafayette, Angel Bob. And off we go with Paramax, ladies and gentlemen. 32,000-pound, six-wheel military vehicle. This is a wire demonstration, and off we go. Good try, guys.
Okay, this is the final score. Okay. Yeah. Let me say, this was a video from the first DARPA Ground Challenge that was held in 2004, and no one can finish the challenge, the route. And let me say, I think that it's the one that drive more is something like 5 kilometers or 10 kilometers, something like that. And the whole road was something like 100 kilometers or 100 miles. I can't remember. By the way, okay, it was less than 10 years ago, okay? And now, okay. After less than 10 years, we have these vehicles, these autonomous vehicles. Okay, I'm pretty sure you are familiar with this one. If you don't know it, it's the autonomous vehicle by Google. Okay, they were driving inside normal traffic. They have some state of the United States made some new law to so they can drive inside normal traffic. This is another vehicle. It's from Stanford. They just drive without any perception. They have a very amazing control of the system. They can drive very fast. They can do a lot of very nice things. And this is our vehicle. Okay. I will speak about that in the next slides. Okay. Okay. Sorry. Okay. Let's go to the next slide. Sorry. Okay. Okay. All these vehicles have different characteristics, and there is different challenge. In the past, there were different challenges with different characteristics. We use this taxonomy to explain the different characteristics of this challenge. Okay. First, we have to say that if the route that we have to take is mapped or not. Okay? Of course, if it's mapped, it will be easy, but easier. It's not easy anyway. And you have to see if the scenario is known or unknown, if it's familiar, if you already get there, if you know a lot of things, or if it's just unknown. You don't know where you are going. If you are driving on road or off-road, it's pretty different, because if you are driving on road, you can assume that you are on a flat road. You can assume that you have no hole in the street. You don't have to avoid bushes or something like that. If you have to drive slow or fast, of course, if you drive slow, it's easier. And if the obstacles are static, are dynamic and predictable, and when I say dynamic and predictable, I said, okay, there is a rule, there is traffic rule, and all the vehicles follow the traffic rules. Okay, in Italy, it's not the case. And also in other countries, let me say. And if it's dynamic and unpredictable. So if you are driving in a normal condition, you cannot predict if a pedestrian will cross the road and stop in the middle of the road, or if someone is just cutting in and without any reason and just cut you in and without any idea of the traffic law, or if you are approaching a two-lane stop, if they will use a free lane, free queue, okay, this is out of the law. But I'm pretty sure that you are familiar with that. Okay, so this is the more simple situation, the more simple challenge. And this is the most complicated. Okay. Okay, let me say that the DARPA Grand Challenge, the first Grand Challenge in the desert, so with autonomous vehicle, okay, the obstacles were static. Everything is mapped. The scenario, but the scenario is unknown. You don't know if you have to deal with bushes, with hole, with berms, with tunnel. You don't know anything. It's, of course, off-road. But, okay, let me say, you have to drive slow. Let me say, it's slow. It's, you don't have to go around 100 kilometers per hour. You have to drive up to 60 kilometers per hour, something like that, 70, 80. You know that in the desert it's not so, you cannot drive so fast. Okay, then DARPA also held the Urban Grand Challenge. The Urban Grand Challenge is different. It's made in a simulated city. It was a closed base, aeronautic base, if I remember well. And, okay, everything is mapped. The scenario is familiar. It's on road. You draw slow because it's in the city. And you have dynamic and predictable obstacle. There were some stuntmen driving the car. So there is traffic, real traffic, but the driver were just follow the rules. They just know the rules and follow the rules. And okay, so we have another kind of challenge. Okay, this is the three different approach. Here with this car from Stanford, we have static obstacles. Everything is mapped. You are in a familiar scenario. You can drive on road and off road, and you can drive very fast. This is an approach. It's mainly based on the control of the vehicle. It's not our purpose, our main purpose. Okay? This is the approach of Google. They have everything mapped, of course. They are in a familiar scenario. They are on road. They drive fast, but they have dynamic and unpredictable obstacles. So they drive in the normal traffic. And this is quite complicated. And about our little orange vehicle, okay, we have no map. We are not in a familiar scenario. We are on road and sometimes off road, but in a we didn't approach a desert or something like that. We are on, let me say, very rural road with no asphalt on the road. We drive slow, but we have dynamic and very unpredictable obstacles, let me say. Okay, so this is the experience of my lab. Yes, my lab. And this is Argo. It was used to make a demonstration of autonomous driving in 1998. Okay, this is the vehicle that we used in the DARPA Grand Challenge in 2006 and 5, sorry. And this is the one that we used in the Urban Grand Challenge in 2007. You can see that they are huge vehicle. Okay, and this one is another vehicle. It's not built by us. It's built by Seoul National University in Korea. And in Korea there is a huge interest in autonomous driving. And Hyundai already held 2 competitions of autonomous driving. And we participate with the Seoul National University team. And yeah, let me say, it was an amazing experience. And we were very surprised about the interest of a car manufacturer on this thing. And also, the government of South Korea is very interested on this. It's pretty strange. It's not strange, but it's very interesting. Okay, so we have a lot of experience with autonomous driving, but are the systems reliable? This is the question. Are the systems reliable? We can trust on that. Okay, we need a long test. We need a huge number of different situations to test. Okay, so the idea was to have a test expedition. So this is all the people working to prepare the expedition, and also being in the expedition with different rules, with different someone that developed the system, someone developed the vehicle, someone just drive the motor vans. Also, this is our 4 electric vehicle that we use for a very huge test. Okay, this is the whole expedition. We have the 4 autonomous electric vehicle. We have 4 motor van. We have 2 truck. And because we have to, as the vehicle are electric, we can use it only for short period, only for 100 kilometers. Then we have to recharge. So we use 2 at a time. Then we put the other on the track. Then we recharge all the systems. Then we put, we exchange again. So it's a huge expedition. And it was quite long, let me say. We start from Italy, and we go through a number of countries, 2 continents, and to reach Shanghai for the Expo of 2010. And let me say, as you see, we do also some zigzag, some because of sponsor. Okay. Okay. As you can imagine, we approach very, very different situation, very, very different road, very, very different way of driving. Because in Italy, here in the first part of East Europe, you have normal road as you have here in Spain, as I'm used to drive on. And when you approach this area, also this area, it's quite different. It is quite different. Okay. So we want to test our system, and oh, sorry. Okay. Okay. The system that we are testing is leader follower, stop and go, waypoint following, vehicle detection, lane detection, generic obstacle detection, pedestrian detection, ditch and berms detection for off-road driving, panoramic viewing system, and terrain mapping and slope estimation. Okay, let me say, it's a number of things. We use both camera and laser, so we have a number of things to test. So we didn't use the whole set of this whole system together. As this was a test, we decided sometimes to use the lane detection, sometimes to use the laser, sometimes to use the camera, sometimes to use laser and camera together, sometimes to detect to use the leader follower, sometimes to use the lane. It's a test, but we drive for a long period, for a number of kilometers. Okay. And we also record all the data that we, during our trip. So we have data from the camera, from the laser scanner, from the GPS. So we have a huge and, let me say, unique database. And we also have a graphic user interface just to tag the data on the fly. So if you are approaching, if it's raining, okay, it's raining. If it's sunny, it's sunny. If there is some dust, okay, dust. It's very simple, but it works. And okay, we are searching for a situation in which there is dust. Okay, you have dust here, here, and here. You can choose. Okay, it's a huge work also to search in this data. And also to use this data is not very simple because you have to search for the correct sequence, and it's not so simple because it's a huge amount of data. But okay, we have it and we can use it, and we already use it for some tests. Okay, this is the sensing suite of our vehicle. Okay, we have 7 cameras. Here we have a stereo pair. Here we have 3 cameras, and we use it for panoramic view. If we are following the vehicle in front, he can also make tire curve, and we don't have problem. We have also 2 cameras in the back if we need to go back. And I think that we made it, not so frequently, but we made it during the trip. We have a 4 laser scanner. This is one 4-plane laser scanner. This is a single plane laser scanner here, and another on the back. It was not installed on no, sorry. The one on the back is not installed. This one is here for ditch and berms, for the detection of the profile of the road. A GPS with IMU integrated. We have a vehicle-to-vehicle radio integrated in this GPS. And plus we have additional device, like this one that you are seeing here is for internet connection using satellite. It's and also we have this tool that measures the atmosphere, the CO2 in the atmosphere, in the air. So we report about the air in where we are driving. So it was also interesting, and I think that's it. Okay, this vehicle are electric, and we also take care about the control of the vehicle, of the automation of the vehicle. Here we have a motor that moves the steering wheel. We have a board that controls the engine, the acceleration. we have another motor that pull a wire and push the brake. So it was a huge work, let me say. Okay, as we have no map, we have a leader vehicle that defines the route. This is the first option. Okay, so we can perceive the leader vehicle. Okay, and we have a route definition, but we also perceive the situation, the obstacle, the lane, and so we can refine the position. If we cannot see the vehicle can send us, using the vehicle-to-vehicle communication, some GPS waypoint, and so we have the route definition. Okay, here we have 4 videos that show some not normal, let me say, cases that we have during the, sorry, wow. Okay, once again. Okay, during the trip. Okay, this one was let me say off-road. They were building the road, so there was no asphalt. Here we are in mountain, pretty difficult, let me say. Here is raining, okay? And it was not so easy to drive in such a situation. And I'm a little afraid in this case. I'm ready to take the control, because actually it was very difficult also for us to see what's happening outside. You can see it. But the system is still working. Okay, it's not working very good. It's not working perfectly, but it's working. And here we are working without any vehicle in front. We are just following the lane. This is another thing that we want to test. And we have to wait that we have the lane marking to test it, because yeah, otherwise we have no information. Okay. Okay. Our main idea is to use the stereo system to drive this vehicle. So we developed this system that is able to perceive where the road is, and also to perceive the obstacle. So I will show you some nice results that we get. Here we are very close to Shanghai. We are approaching Shanghai, and there is a lot of traffic. Okay, we are driving very slow. This is the leader vehicle that is recording the images, because the other vehicle has no possibility to record the images, because all the processing is used, all the PC is used to control the vehicle, of course, to sense the environment. Okay, so you can see that we are able to detect a lot of different, also in traffic, a lot of different situations. This is off-road. Okay, if you see, okay, we can also detect the this ground, I don't know how to call it. And here will appear a negative obstacles, a hole in the road. Okay. No? Okay. Sorry. Okay. No. okay, even in case of dust, smoke, okay, we can have some perception. It's not so robust, okay, let me say, because, okay, if you are familiar with computer vision, if you have dust, if you have smoke, if you have a fog, you can have a lot of problems, but it's still working, okay. And once again, the rain. As you can see here, we have also some drop on the in front of the camera. Of course, if you compute the disparity behind the drop, you will have an error. But where there is no drop, okay, we can find correctly the obstacles. It's not so precise, of course, because we have less information, but it works. Okay, here where you see the black is because we cannot compute correctly the disparity, of course. Okay, and also we tested in the dark. Okay, this is not completely dark. Okay, it's, let me say, at dawn, maybe. Okay, and we can also detect the obstacle in the dark. Okay. So we made this huge test. And this huge test is something like 14,000 kilometers. And we tested a lot of things. But, okay, let me say about vehicle actuation, the driverless technology take care about environmental sensing, intelligent decision, and vehicle actuation. Our main expertise is in environmental sensing, as I already showed. Our main expertise is in computer vision. We also have expertise with laser scanner, with all other sensors. But our main expertise is in computer vision and environmental sensing. We also made something about intelligent decision and vehicle actuation. But our main expertise in environmental sensing. Okay, this is the vehicle that we are using right now. It's quite different from the one that I show you. Yes, this is not the final version. I will show another picture with the final version of Brave. And the Brave stands for Brain Drive. And yeah, this is our vehicle. As you can see, there is a big difference. And okay, I will show you also here. This is the difference of Brave with other vehicle, autonomous vehicle. We take a particular care to the integration of the system. Here is the camera, it's quite invisible. Here in the rear mirror, there is another camera, it's quite invisible. Here the camera, laser scanner, another laser scanner. This is our idea on how to work with autonomous vehicle. We think that if we want to put this vehicle on normal road, we cannot have something like this, okay? Sometimes here you have this terrible, let me say. It works very nice. It's very effective. You have a lot of, but you cannot drive in normal traffic with this. They will not allow you, I'm pretty sure. And the other difference that you can see that we are not using this nice tool. Are you familiar with that? Okay, this is a laser scanner. Is a 54 layers laser scanner rotating 360 degrees, and it was amazing. And during the urban Grand Challenge, maybe also during the second DARPA Grand Challenge, they developed this system, and everyone wants that. Because it's amazing. It gives you a number of information, a number of points. It's rotating 360. You can look all around. You can look all around. You have information on everything around you. Okay. This is not our approach. We think that if we have this one on the top, it's not so easy that a car manufacturer want to buy your vehicle. Okay, this is very helpful. This works very good. But okay, this is another approach. We want to use a low cost and highly integrated sensor. And instead of use expensive and invasive sensor. I don't know if you know, but yesterday or in this week, CMU University, Carnegie Mellon University, announced that they presented their vehicle. It's highly integrated. It's very nice, and they are going in this way. Let me say. The integration of all the sensor, of all the systems, and invisible. It will be invisible. And this is very nice, let me say. Okay, this is the information that we can get from the LiDAR-based sensing. A number of points is 1.5 million 3D points per second. A number. You can see this is vehicle overtaking us. This is trees. I can. Sorry, I want to see it again because it's interesting to see that you can see all around. You see very far away in front, very far away in the back, very far away on the left, on the right. Okay, it's amazing. It's amazing. You can perceive also the vehicle on the other part of the road. It's, wow, it's very interesting. Our approach is quite different. Okay, this is an image from Kitty database. I don't know if you are familiar. This is a database used for to test the system of intelligent vehicle system, let me say. Okay, this is an image. Okay, if you can see here, okay, there is this one is a traffic light. Here you have a traffic sign. Here there is a pedestrian. Another pedestrian here is very difficult to understand it, but this one is quite visible in the image. It's very far away, but it's visible. Okay, if we compare the, this is the LiDAR information. This is the vision information. Of course, the LiDAR, okay, have all this information that we have not with our camera, because we cannot see 360 degrees. Yes, of course. Okay, but if we compare this area and this area, okay. Okay, here we have this information, and here we have this information. Quite different, I think. Okay? Here you have the idea of the color of the vehicle, you have the idea of the distance. But if we go also here, okay, here you can see this one is a traffic light. It's very far away. I'm not sure that you can understand this one is a traffic light, that the light is red, that this one is a traffic sign. I'm not sure. I'm not sure that you can understand this one is pedestrian, but you have enough point to say something. Okay. In this case, we have only this information. It's quite different. Okay. Let me say, this is a completely different approach. Okay, this one is 360 degrees. Okay, it's very interesting. But here we have more information. You can see here, this is a vehicle. Yeah, wow, you have no information here. Of course, a completely different approach, but we said that, okay, this one has some, it's good, it works, but also this one works, and work in a different way. Okay, I will show you this video. This is a 3D reconstruction, and we are using a 640 by 480 pixel image for computing the disparity. Okay. Okay. This is we are going into the 3D world. Okay, we have 270,000 of 3D points. We have X, Y, Z, and color. Okay. This is the image that we used. The disparity image that we used to, sorry, go back. Sorry, yeah, go back. Okay. This is the disparity image that we are using to compute this one. As you can see, we are computing a very dense 3D reconstruction, disparity computing. Of course, using this, we can compute this disparity real time. Okay, in this case, we are using a 1024 by 768 pixel image. And of course, this one is not so quick to compute. Okay, we are, I don't know if with a normal PC we can go real time, if it's enough, we have enough computational time. But computational power, when we are close, we have a very amazing result. Of course, the black area is where you cannot see nothing. You can see nothing. Yeah. This is the projection of the 3D point with the color in the world. And yeah, we just move inside this world. This is just to show. And you can use this information not only to detect the obstacle, but also to classify the obstacles. Okay. Okay. So we can make the terrain mapping, as I already said. I will go. Okay. Here we are in a rural road. All this chessboard, let me say, is computed by the using the disparity. Okay, we can move inside. You can see that here we can detect these negative obstacles, also here. Okay. Okay, we, of course, as already shown you, we can also detect the obstacles and the free space. Let me say that all this is free space. We have here the obstacles. We can drive in this area. This is the campus in Parma. Without snow. Here also, even if we have some shadow on the road, we have no problem to detect the road. Okay. We can also detect the pedestrian here. Okay. Okay. And okay, once again, we can. This is another video. You can see that this is taken from a different position. The camera was very, very high. It's something like 6 or 5 or 6 meters, between 5 and 6 meters, because we want to test also this situation, and we can detect the position of the obstacles. Here we can detect this area. We can detect the vehicle. We can detect the free space. Okay, pretty different situation, pretty different point of view. Okay, so I show you that we have a nice stereo. We are able to make a very interesting and huge trip from Italy to China. And we were very proud of that. And so we decided, no, I'm joking, but we decided to make this proud car test. That means a public road urban driverless car test. And let me say why we decided to do that. We tested our system in Italy during all the trip, in Russia, in China, in Kazakhstan, Ukraine, a lot of different. But, okay, let me say, we have a leader in front of us. In some special case, we need to trust the leader, and we were not able to manage all the situation. We were not able to manage the roundabout, the traffic light, but this is not good for us because this is not real driving. Okay, so we want to test our system in very real situation. This is so we want to test in public road. And this was amazing. And let me say, it is also the bureaucracy for this was amazing. Was huge because you have to ask to the government, to the police, to the city, to everyone, to everyone. And let me say, I will show you the vehicle. I will talk about the test, and I will go into the details. I think that you are interested in the details because I will speak about the architecture that we used for this test, the system, the perception system that we developed, and I will show you some video also about that. Okay, this is a different approach. So we have a map. During previous tests, we always said, okay, map is not our job. We just want to drive without map. Someone else will take into account the map. Okay, autonomous driving without a map is, let me say, impossible. Because the first question is where I want to go. And if I don't have a map, I don't know. And the second question is, how can I get there? And if I don't have a map, I have no idea. I can follow the lane. I can follow a leader. I can maybe turn on the second right. Okay, I can do that. I can do that. But where I'm going, I have no idea. Let me say, we need a map. We need a map. And we work in familiar scenario. Okay, we work in Parma. And we already made the same route a number of times during day, during night, with rain, in sun, with sun in front, a number of tests. We drive fast. Let me say, okay, fast. It's not so fast as you can imagine. We are not driving 130 kilometers per hour. But we drive in the motorway. The speed limit for the motorway is 90 kilometers per hour. And we, between 70, in some part 70 and some part 90, we drive at around 70 kilometers per hour. And during the test, we also drive faster. But during the test, okay, it's not the case. And we manage dynamic and unpredictable obstacles. That means that there is the vehicle that are on the road is not our vehicle. There is no one that closed the door. There is no the road. Sorry. There is no one that manage the pedestrian crossing. Okay, we were there just to be sure that no one just makes something unsense, with no sense, just like running inside the car or something like that, because, let me say, we were worried that this could happen. And, of course, we manage complex situations and complex maneuvers. Yes, okay. When we speak about environmental sensing, we know that we have to sense, of course, the static obstacles. Okay, this is the first thing that we have to do. If you have something like a tree or a guardrail or something like that, we have to sense that. You have to sense, of course, the obstacle in front, vehicle, pedestrian, in this case there is a vehicle. Also the one in the back. Okay, let me say, this is very useful if you are driving in reverse, in rear gear, in back gear, but okay, it's not so, in our case it's not useful. You have to detect a vehicle here that is approaching, that is overtaking you. You have to get also the vehicle that's coming from the other side. But if you are on the second lane, you have also to detect the vehicle that are approaching you here, in the right. And again, this is a junction. This is a vehicle approaching. Of course, here you have your stop line. You have to stop. You have to perceive also this vehicle. And if you are on a junction, another junction, this is a different junction, you have to perceive also this vehicle. A number of things that you have to do. Okay, if you have your 360-degree LiDAR here, okay, you see everywhere. Okay, you cannot see very close here in this area with this kind of system, but you can perceive everything. Okay, in this case, it's not our case. Okay, we want to use our camera. Okay, so we use this camera here to perceive, let me say, the lane marking, the traffic light, the pedestrian crossing, the stop line, the pedestrian. Okay? We use a stereo system to perceive the obstacles in front. We use this camera for the junction, for the roundabout, to detect if some vehicle is approaching. And we use also this camera because we have a junction to a motorway. So we need to see if a vehicle is approaching from the back. Okay, we didn't use these cameras. And let me say, even if we have this camera, okay, we didn't use it. And the PC were very busy, even if we didn't use these cameras. We don't use the back camera because we don't want to go in rear here, and we didn't use this one because we just stay in the first lane. We didn't. We decided not to overtake the other vehicle. We didn't use this one because there is no junction in which we need to perceive also the vehicle arriving from the right. Okay, let me say, the application, the system, the algorithm that detects the vehicle is the same on the right or on the left. We just want to, let me say, not to use other computational time, other computational power. And so we decided to reduce our system. So we also have a laser, of course, because we really need to have the possibility to see the obstacle with two different systems. Because if, for some reason, the laser, as happened during a test, had some problem, we have to use the camera. And on the other hand, if for some reason the computer vision doesn't work, and this happened because we go into a tunnel, and for some very few moments, we are blind. We were blind. We need to use the laser scanner. And we needed to use the laser scanner also because it helped to perceive the obstacle very close to the vehicle. That is difficult to see with the vision. And help to have a almost 360 security belt around the vehicle. Okay, so we have a free laser scanner. This free laser, very small laser scanner from Okuyo, and they are they can detect up to 30 meters, and they are reliable in up to 15 meters, let me say. And we have three, one here, and one in the back. And we also have a 4-layer laser scanner here in the front. And let me say it helped a lot. Okay, this is the internal configuration of Brave during the test. We have 2 passengers. And this one was my boss, Professor Broggi. And this one was the head of the university. And okay, I was quite afraid when we were driving. Okay, and this is a technician. Actually, it was me. And this is one of my colleague of mine, and it's okay. We call it safety inspector. It's just being here, looking. Everything is working as we expect. And finally, it is vacant. He is vacant because he left in the last 300 meters, let me say, just to make the show. He is outside the vehicle, but also during the complete test, he is just looking and, okay, everything is working. And okay, so we also record some image during the test. There is a camera here, and also we have a vehicle back, and we have a camera here, and we have also the emergency stop. Okay, both the people here were able to stop the vehicle. But if for some reason something went wrong, there is another emergency stop here. So just pressing a button and the vehicle will stop. Okay, this was not the case. Okay, this is the test scenario. We start from here, and we go all this, and we are right there. Okay, we start from the campus. Here the road is closed, and then the very first part, the road is closed because we have to manage everything to start the system. There is a very narrow bridge that it was not possible to take with a vehicle that is coming from the other side. Then there is the first part, the rural road. Okay. Then there is this freeway, motorway. Okay. Here we have the junction between the two freeway in Parma. Then we go into urban to arrive to the final destination, that is in the city center. Okay, the first part, the rural road, is quite difficult because we have two-way and narrow road, and the maximum speed is 50 kilometers per hour. Let me say, the lane width are about 3 meters, and even if it's normal for us to drive in a 3 meters lane, it's not so easy for an autonomous vehicle because you have to be sure that you are very in the center. It's curved, it's narrow, and you have a complex roundabout. I will show you this image. Okay, this is a case, a vehicle coming from the other side, our autonomous vehicle. It's not so far away, let me say. And this is the very complex roundabout. This is not a round. It's something like, I don't know how to call it, a beam, and I don't know. And we have to make something like this. Okay. When we approach this roundabout, we have to approach it very slow because we have to make very tight curves. It's quite difficult for us. Okay, then there is the freeway. It's a 2 or 3 lanes with a maximum speed. In some part is 70 and some part is 90 kilometers per hour. And we have difficulties because there is long tunnels, narrow ramp after tunnel. It's okay. This is the tunnel, and here you can see the ramp, and because this is the junction between one freeway and the other. Okay, then there is the urban road. Okay, the urban road is full of different things. We have 5 roundabouts, 7 pedestrian crossing, 1 traffic signal, 1 tunnel, 1 giveaway, 2 speed bumpers, and very high speed bumpers. So it's quite complex. So the characteristic is that there is heavy traffic, there is roundabouts, pedestrian crossing, traffic signal. The difficulties were that very narrow road. In some part there is very narrow. Vehicle parked along the road, pedestrian, bicycle. A normal city. No. Okay. Okay, this is one of the roundabout. We are arriving from here. Here we have the speed bumper, the stop line, the giveaway line. Then you have to make this one. Here you have another speed bumper. It's not so simple. This is another one. You are arriving here, and you are going very straight. Then there is this. You are to pass under this the train. the railroad. And here is now the final part. Here you have the pedestrian crossing, then the roundabout, another pedestrian crossing, quite difficult. Here is the junction, and this is the tunnel. Okay, you are arriving from here, this is the tunnel, and you exit here. Okay, the results that we obtain is that we drive about 13 kilometers, 3 kilometers in urban area. We drive in about 18 minutes at 11 a.m. on a working day, and no human intervention. Okay, this is some video that show you. This is the start of the system. Okay, now we start manually. Okay, then I press the button. Okay, and we start to drive. Here is from the vehicle that will be in the back, that was in the back. Okay. Oh, yes. As you can see, that this bridge is very narrow, and so we close the door, the road here. Oh, sorry. Here we have the first roundabout, the strange roundabout, let me say. And okay, we arrive. We see that we can go into the roundabout. We are driving inside the roundabout. You can see how the steering wheel is working hard here. Here we have a pedestrian crossing. No one is crossing. We are going. Okay. Here we go inside we merge the freeway. We merge into the freeway. Okay. Sorry. Once again. Okay. Here we are merging to the other freeway. So there is this vehicle that overtakes us, and we have to stop. This guy was in a hurry. Okay, so we start again to drive normally. Right now we are following the lane. We have both the information from the GPS and the lane marking. Oh. Okay. Here we have the first, I think, yes, it's the first roundabout. As you can see here, you can also have a vehicle overtaking you. This is not the case, but we also think how to manage this thing. As you can see, we wait, and then, okay, let's go. We have to be very careful. Here there is another pedestrian crossing. Okay. Once again, another roundabout. This is it's complex because here we have also this bus driving here. Okay, when we understand that it's not dangerous because it's going on this way, okay, we decide to start. Let me say that this is okay. It works. It's wow. we were lucky because if someone is just behind the bus and want to overtake, I don't know. But by the way, okay. Also, the other vehicle can slow down. Yeah. Okay, sorry. Another roundabout. We arrive here, the speed bumper. We stop. Someone is approaching. We decide that here is not dangerous. And we start to go. Okay. Okay, this is one of the problems that I already mentioned. Here there is a tunnel. All the vision here, let me say, is blind. Also here is blind. As you can see, everything is white. Okay. Okay. This is the internal camera, of course, but more or less the same happened to the camera. And here we are able to detect the traffic light here. I'm very happy here because this was one of the parts that I write about the code that I write for the demonstration. Okay. Okay, let me say, I already said that we are not, our expertise is not in the control of the vehicle, so we are going uphill, and so the vehicle is not very comfortable to stay stopped, and so move sometimes. Okay, this happened. And finally, okay, here we have a junction. Once again, we are able to see that, okay, we approach to the pedestrian crossing, no one on the pedestrian crossing. We go to the junction merging, we stop, and then we start. We are driving very slow here. Then my colleague decided to go away. No, sorry. I was trying to say to all these people, go away. Okay, all these people here. Okay. And finally we arrived. A number of policemen and people watching and saying, what's happening? And someone said, okay, a new soccer player has arrived in Parma. Okay, this is when we turn off the system, the wipe washer, just. And also the horn, a lot of different. Okay. We will take a little break, and then, okay, now we can go into detail. If you think it's okay, we can take a little break. Okay. Okay.